Hey guys, we'll just be going over organic chemistry today with Sn1, Sn2, E1, E2, and E1CB. So this is just going to be a general overview with the most important information, and they'll probably cover most of the information that you guys will probably be given to on the test. And so this will be a short, quick guide, but it'll be very informal, not informal, it'll be very informational. And you definitely get most of the stuff that you have questions on here. And from what I recommend is that you understand the mechanism first before you try and do the practice problems, and then try and apply what you know from the mechanisms. So yeah, so let's get started. As a table of contents, we'll just go over Sn1, Sn2 together, and E1, E2 together with E1CB, and we're gonna go over how to choose a mechanism and practice problems. Yeah, so let's go over Sn1, Sn2. So this is a cute diagram that I went over before. Um, that over before my students, and this is a very fun way to memorize Sn1, Sn2. So in this case, that bed is our electrophile with the gray cat, our leaving group, and in Sn1, the cat leaves by itself, right? Leaving group leaves by itself, and the orange cat, our nucleophile, takes over. Woo, he's happy, right? Crazy. In Sn2, the orange cat is just gonna attack him from the back. He's gonna sneak attack it and kicks out the leaving group. And the nucleophile, our cat, orange cat just stays there happy. I mean, orange cat behaviors. What can I say, right? Yeah. Yeah, so let's go over Sn1, Sn2 in conditions, right? So Sn1 the condition, the nucleophile is usually tends to be weak nucleophile, and it prefers tertiary, then secondary, and really hits primary. And Sn2, the condition is the opposite. So it's more strong nucleophile, first primary, then secondary, and really hates tertiary. So it will never do tertiary, and Sn1 will never do primary. So Sn1 loves to do, does it in 2 steps. Sn2 does it in 1 step. The 2 steps for Sn1 is forms a carbocation and a nucleophile attacks, like you've seen in the cat. Sn2 does a backside attack in 1 step, and it kicks out the L group as soon as it attacks, right? Another way that people that I like memorizing it is that pretend that it's similar to a video game with a ninja, right? Nucleophile, ninja, both start with N, pretty much easy to memorize. Um, and as a ninja, you like to do attacks. You like to attack someone, right? And as a ninja, you want it to be, so this is going to be applying to Sn2. You want it to be a very strong ninja, right? You want him to be buff, aka strong nucleophile. Um, and when you attack, you don't want to attack the tertiary, right? See how there's 3 carbons here, and there's a chlorine. That's the leaving group. And these 3 carbons here are pretty much your guards, right? They're going to be acting like guard, protecting this carbon, right? And as a ninja, there's 3 guards. Boom, scary. I don't want to attack there. Oh my God, 3 guards. Can't attack. Impossible, right? And you don't want 3 guards. You want something that is easy attack, aka someone with 1 guard, like a primary, right? 1 carbon attached. Boom, easy to attack, right? And as ninja, you don't want the enemy staring at you, right? You want him away from you. So you like to prefer backside attack, hence inversion when you attack. So, and now this is a graph that you guys have to learn. And I believe you guys did go over it in with the professor. And this is you don't have to memorize the graph itself, but it's good to know which one's a slow step, which one's the first step. Um, in Sn1 reaction, uh, the reaction is first order, and in Sn2, it is a second order. Give me 1 sec to double check that. Yeah, hence the number 1 and 2. Um, in the Sn1, you have to know that the slow step is making the carbocation. So you're gonna go boop, 1 over the first step. So it's a rate limiting transition state. Please memorize that. There's always gonna be questions like, oh, this is a rate limiting transition state or something like that. It's true or false, basically. And this is one of the things that you guys must know. And the second step, which is also slow, but not as slow as for the making the carbocation, is a nucleophile attacks, and boom, it becomes your product, right? And in Sn2's case, the transition state, not the transition intermediate, the transition state is just lined up, this carbons are just lined up as a planar and with a leaving group here, and the nucleophile does backside attack, like we discussed before. Yeah. So yeah, let's continue. Hopefully that helps out with slow steps and what determines what. Yeah, so let's get on with E1, E2, and E1CB. Right now, this is just a generalized form. So we'll discuss more in detail about little intricate stuff determining which one happens. So right now we're just going over the mechanism. So yeah, so E1 and E2 conditions. E1 is weak base and prefers a stable double bond if possible, right? And E2 prefers a stable double bond if possible. Same thing. What I mean by prefer stable double bond, I mean that if it could be secondary, it could be a secondary, it'd rather do that than a secondary primary double bond, right? And it wants to have a strong basis. And so like Sn1, right? This happens with 2 steps, and E1 happens in 2 steps. So anything that contains 1 happens in 2 steps. Anything that contains 2 happens in 1 step. It's just the opposite, right? And as its first step, it forms a cation, a carbocation, and then the nucleophile attacks the H that's next to the carbon, next to the leaving group. So basically, this is the leaving group. It's going to attack the H that's next to the carbon next to the leaving group. So the leaving group's here, is next to it right here. So this H leaves, and then it attacks the H here. The leaving group leaves, and attacks the H, and boom, forms the one, right? And usually it technically could take an H from here as well, but rather take an H from here to form most stable double bond. It prefers a stable double bond. So it wouldn't form double bond on the other side. Hopefully that makes sense as well. So yeah, so E2 also just happens in 1 step, and what it does is that it must have H that's anti-periplanar, aka very similar to a backside attack. Very much like the ninja again, right? So again, one strong base, boom, the strong base there, and it attacks the H that is directly almost anti to the LG. So basically, as you can see here, this BR is like in the front and this H is anti, like towards the back, right? And so what it's gonna do, you kind of want to draw in this formation. So to make it easier, this base, strong base, as you can see, the negative charge on the O, takes this H and boom, kicks it off like that. And this bond between H and C will now become your double bond between 3 and 2. And you see how 4 and 1 carbons, they're both wedged. Hence, they'll be cis when you draw a double bond. And 5, the single dash one and with a dash H would be on the same side as well. So that's an easy way to do it. And make sure you do it this way because the stereochemistry in this case matters. And like Sn2, it matters. The only time it doesn't matter is when is in Sn1, where Sn1 you form a carbocation and it can do backside or frontside attack up to it. So you could say it's racemic. So yeah. Yeah, so now let's go into E1CB. And so E1CB is you want a pretty good base, and it does not really care about a leaving group. So in the other cases, you want at least a stable leaving group to leave. So in this case, it does not care about how weak the leaving group is. It could even be a OH. OH is known to be a horrible leaving group. And E1CB is like, I don't care. I can still kick you out. Why can I kick it out? It's because this also happens in 2 steps, hence E1. Right? But instead of forming a carbocation, it forms a carboanion, right? So what I mean by carbocation is that this base actually starts off the reaction. It takes that H first, and then it leaves a negative charge here, and it goes up. So right now we're just drawing a good resonance structure. And usually it's stabilized by electron withdrawal group. In this case, the C double bonded O. That's our electron withdrawal group, right? And because it's stabilized by that, it do E1CB. And in most cases in your test, it's just going to be double bond C and O. Usually, I'm not saying it's always the case. In some cases, it's not. So if you want, you can always ask me more about it in class. But yeah, if not, don't worry about it. Talk to me in class, and I'll definitely give you more example. But for most cases, it's going to be C and double bond O. And I have a feeling they might drop it on tests because they tend to do stuff like unpredictably. And they only went over this guy only a little bit. So I have a feeling that it might be on test. Don't quote me on it. It could be. And for here, you want to know that this is the fast step where it takes the H. The slow step is eliminating the leaving group. Yeah, so you do protonate for carbocation and you form double bond. Hopefully that helps you off E1CB, and that's pretty much all you need to know about E1CB. So I hope you guys aren't too panicked about that. Yeah, so let's go on with the factors and how to determine what's what, right? And what I mean by factors as well is that the speed. There's some question on your practice that says, oh, which nucleophile, which electrophile together makes the fastest reaction or the best reaction, right? Or requires the least amount of energy. In most cases, you want a very strong nucleophile because it's probably gonna be talking about Sn2. And so a strong nucleophile versus a weak nucleophile is that the strong nucleophile is very unstable and it wants to attack right away. Because if it's a weak nucleophile, it doesn't want to attack. It's like, huh, I'm stable, I'm lazy, and I don't want to attack. There's no point. I'm stable by myself. I don't need anybody else. Boom, easy. And electrophiles. So electrophiles contains a leaving group, and you want it to be a very stable leaving group. And depending on the conditions of whatever reaction you're doing, your electrophile must play a role. So for example, Sn2, it, like I said before, very much prefers primary. So it much rather prefer primary. But let's say if it was next to a tertiary group or even on a tertiary, Sn2 really hates that. So it would never even happen. So that's why it makes it the worst leaving group, right? Or worst electrophile, which is probably going to be on some of your questions. And so as in leaving groups, stability. You want a stable leaving group, so you want a big leaving group, usually. So in this case, you could still use what I taught you before with both nucleophile and electrophile leaving groups. You can use the acronym cardio. I believe I did go over it in one of my other videos, so you guys could check that out as well. And so yeah, so you could use that to determine stability. And so we'll be talking more about solving later on with protic polar and aprotic polar. This will also be playing a big role in your tests when you when you have some questions that revolves around solvents. And not only a nucleophile could be weak or strong nucleophile, they also be weak or strong bases. A weak base really needs the H, so it's very like the weak nucleophile is very unstable. A strong base is could be a strong nucleophile, and it could be also be a weak nucleophile. But strong base, it's very unstable and needs H, right? And weak nucleophile is stable already, doesn't need a H like the weak nucleophile here. Weak base is like the weak nucleophile, so they're pretty much like the same. While strong base, it's not always a strong nucleophile, and it could be a weak nucleophile. And a weak base could still be a strong nucleophile. So let me just go over that again real quick. So weak base, stable by itself, doesn't need H. Strong base needs an H, right? And there's going to be a way to determine that later on. So types of nucleophile, you have weak nucleophile, weak nucleophile, strong nucleophile, weak base, and strong nucleophile, strong base. And usually basicity wins over stability in most cases with this, especially if it's secondary and tertiary. Primary tends to be the nucleophile takes over. We'll go into that like now. So, nucleophiles. If it's weak, it usually has no charge and it doesn't want to attack because it has no charge. It's like I'm stable. No need to attack. Bye. Strong usually is charged. It can be shown in ionic pairs like NABR. For example, NaN3, an ionic pair, NaOH, ionic pair, NaOMe, ionic pair. Yeah. So as long as it has like a negative charge, it usually should be a strong nucleophile. And so how can you tell between strong base and strong base and strong nucleophile is that is for example right here you can see that this O is stabilized by the oxygen here. So because it's very stable by itself, it doesn't really need an H, but it still has that negative charge though, so it would be a very strong nucleophile, even though it's very stable. So this you could even make an argument that it's less nucleophilic than some of these, depending on the solvents. Uh, so, yeah, that's the way to determine between those. So these guys, you could just copy down this, and this will probably help you during the test as well. So this is a good thing to have on your cheat sheet. Although I have more example, as you just see, I gave you a sneak peek on my next slide. That is definitely gonna also help you on the test. So please try and copy it down. Um, yeah, so let's talk about this bottom thing. Bulky versus not bulky. So remember how in E1, E2, say it prefers to be stable double bond if possible. So in some cases, you have a very bulky base for elimination. And so basically like a ninja is very big, very big. So if it could take an H, if it could take an H, that's um that's easier to access, so like less stereo, where the big ninja could fit through, then it would much rather take the H, right? It would much rather go for less substituted carbon with an H that's anti, especially in E2 reactions. So that's how bulky promotes. So right, bulky usually promotes E2 like it says here, and it prefers the substituted side. So it doesn't form the most stable double bond because it's bulky. An example are torpedo. Torpedo is definitely going to be the most important one. Yeah, so this is another example. Just make sure you kind of memorize this graph, or if you're not going to memorize it, at least put it down on a paper. And although it's not included here, heat would usually tend to make this part, even though it looks like 50-50 now, if there's heat, E1 is usually preferred. Elimination is usually preferred if there's heat. So keep that in mind. Yeah, so this is also a good example. So you can always pause the video here and then just copy this down on your paper. And you can make like a mix between these two. Yeah, so let's talk about solvents, right? So we have protic and aprotic, right? So protic has H bonding, aprotic no H bonding. And because protic has H bonding, it's going to be surrounding both the nucleophile and electrophile shown in this diagram here. Why? Because the H bonding has a partially positive and partially negative, right? This partially negative is going to counterbalance the electrophile and the ion. And this H is going to balance out the nucleophile. Hence, it's going to surround the nucleophile and it's going to stabilize it. So if it stabilizes the nucleophile, like we discussed, if it stabilizes it, it's going to make a weaker nucleophile. So if you have a weak nucleophile, you don't like that because especially in Sn2 and E1, E2, because hey, it makes it slower and nucleophile is too lazy to attack because it's stable. So that's why Sn1 E1 prefers it because it stabilizes it a lot more. And the halogens, this especially affects the halogen nucleophile. I've talked to the professor about it. The solvent should only usually affects the halogen trends for nucleophile. And in this case, because the H bonding does stability, the basicity does not matter anymore. So the bigger the bond here, the bigger the ion, the better as a nucleophile it is. So I, being the biggest one, would take over because basicity does not matter. But an aprotic, where there's no H bond, it only surrounds the electrophile and not the nucleophile. As you can see, it is a naked anion. So this anion is free to attack. So it prefers Sn2 and E2 prefers it because the nucleophile is free to attack, right? And so because there's no H bonding, the basicity takes over in this case. So F will take over and be the best nucleophile here. So basically now it reverses itself. So basicity matters in aprotic. So an example of aprotic is DMF, which you guys learned before, CCl4. Yeah, so let's try some practice problems. So yeah, let's get started. So let's draw it out. Cn minus. All right. So Cn minus, This is a very strong nucleophile, but not a good base, because there's negative charge, but it's not on dirty rule. That's not on N or O, and so you can also do it looking at your cheat sheet, and we know that it's going to attack from the back here, and it's going to attack and push off the CL, and so hence you're going to get this. And just to make sure, it's also on a primary. There's also another way to know that it's going to be Sn2, right? So, and here we have NaOH, so OH, boom, OH minus, right? And so already we know that this is a strong base and there's heat. So although the other graph, if we go back to the graphs, give me a sec, let's go back to the graphs. Yeah, so even though primary prefers Sn2, because it has heat, it's probably going to prefer elimination, right? And although this was not mentioned, because a product does, if it in a competition between Sn2 or E2, it would tend to prefer elimination if it is in a product, even though E2 would generally prefer a product. So in this case, we would say that, hey, it would prefer it would definitely prefer a elimination reaction, E2 reaction, where it would just take an H from here. That would take an H from here. And let's say this was dash. We'll just take it as an H, and it will come down and then kick off the BR, forming this. And in this case, you definitely know that is E2. Right, because that all happens in one step. This is a weak nucleophile and a weak base. So we could basically say that it's either Sn1 or E1, right? But there's no heat. So usually, like if you see in a graph, it's 50-50, but there's no heat. So I would say that go for Sn1, tends to be the case, especially since it's on tertiary. So in this case, it's gonna come over. Oh, not come over first, so this is wrong. What's gonna happen first is this BR is gonna leave as leaving group, forming a cation. And then once a cation forms, only then can this guy oxygen attack. And once the oxygen attacks, it then kicks off H of its own to form alcohol. This is Sn1. And boom, oh, look here again. Negative charge on oxygen, and oxygen is not stabilized. So we can say that, safely say that most likely is a strong base, right? If it's a strong base, I could definitely say that, hey, it's probably going to do elimination, right? And it's probably going to, so this is not too bulky. It's not tertiary, right? This is not tertiary. So we could say that it's not too bulky. So we would probably prefer the most stable double bond. So in this case, it's I is here and it's wedged. So we must find dash H's. So I like to indicate all my dash H's. So we have a dash H here and a dash H here. So which H would you rather take from? Well, like I said, it's not too bulky, so most probably prefer the most stable one. So probably take this H because it's empty. And if this was ever wedged, then it'll always take from the other side. But because this is dash, it's allowed. So probably take from here, and this would drop down as double bond, and I get kicked out. Hence, you get this. So that's E2. And yeah, that's it for the practice. Hope you guys liked it. Take care.